In this video, I'm going to walk through a general overview of our system, focusing on the mechanical design, actuation, computation, and sensing. For a demonstration of our Haptic device, please see the subsequent video. The goal of our project was to create a fully textile-based pneumatic haptic device, specifically a fluidic squeeze band and a fluidic vibrotactor. By incorporating these devices with the sound output of our computer, the device became focused on interactive art. All computation and control was done in a LabVIEW VI, and an NI DAC was used to control regulators and read sensors. Actuation of our devices was performed with voltage-controlled pressure regulators. These regulators have internal closed-loop control to regulate the pressure accurately. The pressure was sent to the haptic device, with one regulator controlling the squeeze band and the other controlling the vibrotactor. The mechanical design of the squeeze band itself is fairly straightforward. Air enters through this nozzle here and inflates these little pouches or compartments. When these inflate, the entire band contracts, causing a squeeze sensation on the arm. This was done by using multiple layers of textiles and a heat press to cause adhesion between the layers. By using paper inserts, it is possible to control where the textile adheres and where it doesn't. By doing this in a carefully designed fashion, you can create pockets that the air can fill. The same technique was used for the vibrotactor, although it was a bit more complicated. The device itself consists of two components, one being this semi-rigid base here, and the way that it gets its rigidity is through these channels where a constant pressure causes them to inflate and causes the entire structure to be semi-rigid. The second device is this open channel here that slides between these slots. Pressure is regulated through this tube here, and a variable pressure causes this thing to vibrate at various frequencies. The technique for that is this open channel is fed to these slots, which causes a kink to form in the channel. This kink has a breakthrough pressure, and when that pressure is hit, the kink propagates, and a repeated propagation of the kink causes the vibration. In this way, when the pressure is increased, this breakthrough pressure is hit sooner, and the vibration increases. The kink propagates faster. Because of this, increasing the pressure to this open channel causes an increase in vibration. The same is true with the squeeze band. Increasing the pressure causes an increase in the squeeze amplitude. Both devices were hooked up to Panasonic pressure sensors, which can be seen here. These pressure sensors were used to give a voltage. These pressure sensors give a voltage reading proportional to the pressure. And these sensors were read on the DAC to compare the commanded pressure to the actual realized pressure. All computation was performed on a LabVIEW VI. This VI, the GUI for this can be seen right here. And so what this VI did is it took the sound output of our computer through a virtual audio cable. With that, it analyzed it using a short time fast Fourier transform to get the amplitude and frequency characteristics of the sound. The amplitude was mapped directly to squeeze pressure through an empirical matching between the voltage to the regulator and the amplitude of the sound. The same empirical method was used to map the frequency components to the voltage commanded to the vibrotactor. Peak frequency was used from the frequency extraction using the fast Fourier transform, and the peak frequency corresponded, the higher the peak frequency, the higher the voltage commanded to the vibrotactor, causing an increase in vibration frequency. We hope this provided a good general overview of our system, and we hope you'll watch our next video for a demonstration. Thank you.